Good afternoon, everybody. So I'm going to talk to you about standard reference methods, but what I thought I would do is focus on HCL, because seeing what Andy was going to talk about, I thought that would be a nice complement to what Andy has talked about. But a lot of the sort of the discussion that I'll put forward, hopefully you'll see, has broader applicability to the other kind of wet chemistry standard reference method documents. And so a lot of the data that I'm going to show you has come from a European metrology program for innovation and research project. That project is called HEROES, and that considers the metrology of HL emission measurements with a view to ever decreasing emissions. And there are really two overarching areas of work under that project. One is looking at the uncertainty of HCl as measured by wet chemistry, so the standard reference method that we're all fairly familiar with. And the other overarching area is looking at HCl by what I guess we in the UK call portable SEMS, but elsewhere are called portable automated measuring systems, PAMS for short. And then the last thing I'll mention about the project, and this is now become commonplace of all grant-funded work, is it's a requirement under our contract that we deposit, respecting anonymity and GDPR, etc., all the data that we collect into a repository. And so I think that's a really kind of positive thing that's happening now of research projects. And so all of the data we collect is going to be there for perpetuity. The 5 badges there are just the 5 partners involved in the project. MPL is lead. I'm the coordinator of the project. So if you want to know a bit more specifically about HEROES, then please contact me directly or make an appointment on our virtual stand. So as mentioned, I'm going to talk about specifically the wet chemistry SRM for measuring HCl, which is described in document EN1911. That method covers both sampling of the HCl from the stack and then the subsequent analysis of what has been collected. And I'm going to talk about the latter part. And try and show you some data to try and understand the uncertainty that's possible under 1911 with respect to the analytical step. So what was the aim of kind of isolating the analytical step of 1911? Well, the work has involved dispatching chloride samples across 2 campaigns. So first of all, across UK analytical laboratories, so a bit of a trial run if you like. And then a second campaign where we've dispatched samples across both laboratories in UK and mainland Europe, so a pan-European study. That first campaign, which was UK only, is complete, and so that's the data I'm actually talking about over the next few slides. We do have all the data back from the pan-European campaign, but we literally just got those data back this month, so we've not had a chance to analyse them. But that should be something we can report on in the future. The aim of the work, and I want to sort of stress this, was not a proficiency test of individual analytical laboratories. That's not what we were trying to look at here. What we were trying to look at, and the aim, was to understand the level of control that the analysis of EN1911 is providing across the community. And so what I'm trying to get at here is that when a sampling team goes to a stack and pumps the gas out of the stack and takes the sample, as part of their role, they have to come up with an uncertainty budget, and in that budget, in that table, they'll have various rows that are due to sampling uncertainty sources, and they'll also have a row of the uncertainty that's due to the analytical step. But the reality of that is, of course, that sampling team is at liberty to send the samples they collect to any analytical laboratory that's 17025 accredited. So actually, the uncertainty that should be going into that budget is the variance across all those different labs, because those samples could have gone to any lab across that community of analytical laboratories. So that's the amount of variance that the sampling team and the measurement is ultimately subject to. So this is what we're trying to look at and tease out here. Okay, so there were two types of samples that were dispatched to try and address these kind of questions. One was we called synthetic, and the other we called simulated real, SReal for short. The synthetic samples were prepared by dissolving sodium chloride in deionized water. Those were obviously all prepared in terms of micrograms per milliliter. If you were to multiply by the volume and divide out by the amount of cubic meters of gas you'd normally sample from a stack in about a 30-minute run, you'd get the following emission equivalent concentrations detailed there. So that's our 0 to 10 kind of milligram per cubic meter range. And so it obviously makes things easy to look at things in those kind of units. Those 5 solutions were each split 6-fold and dispatched to 6 17025 laboratories accredited for chloride analysis in accordance with 1911. The second type of samples that were prepared, the simulated real, the SReal samples were prepared using the stack simulator back at MPL, where we created some 46 odd emission matrices. The vast majority of those emission matrices were on a waste incinerator scale. So HL was varied from 0 to 15 milligrams. And likewise, the other components listed there were kind of varied within what you typically find on a waste incinerator. There were a few matrices that were created going to kind of higher concentrations and introducing some other interferences just to give some additional data. But for the most part, we simulated a waste incinerator type scenario. All those samplings of the stack simulator was carried out by staff qualified to level 2 under the MCERT scheme. For each 30-minute run, each individual Impinger solution was 3-fold and dispatched to 3 of those 6 laboratories who received synthetic samples. The 3 out of the 6 were chosen purely arbitrarily. The point of splitting each individual Impinger solution was to eliminate any kind of sampling bias that might have existed. So all 3 laboratories get the exact same solution from each individual Impinger. So therefore, any variance we see in the returned results is due to purely the analytical step in 1911 and laboratories themselves. The work was blind in that, of course, the laboratories weren't told what concentration of samples they'd be receiving. And also we were, I guess, a bit sort of superstitious about this in that we also dispatched all these samples with full chains of custody so that they would appear as if they'd been collected just in the normal course of routine monitoring work. Again, this was to try and just ensure that we didn't introduce any kind of bias and we got back data that was truly representative of a typical analysis. Okay, so looking across our 0 to 10 milligram range, this is all the returned data from the synthetic samples. And so the Y scale there is deviation from the mean. And so what has been done there is within a batch, within a test number there are 6 measurements returned by the 6 laboratories. And so this is then taking the average of those 6 measurements and then working out the percentage deviation from that average. You might ask, why not do the percentage deviation away from the reference value? Because you knew what that was. You knew what had been dissolved in the deionized water. And equally, we could have done that, but there's 2 reasons why we didn't. One is it'd actually look exactly the same. And the second reason is it doesn't kind of really matter here what you normalize to, whether you normalize the measurements to the mean, or whether you normalize them to the reference value, because what we're really looking at is what is the comparability across the community of laboratories. And straight away, obviously, you can see that's, across all those tests, a fairly relatively tight comparability visually. One kind of way of measuring that is to look at the uncertainties, and all of the uncertainty bars on each black square, on each measurement there, are provided by the laboratories themselves. And so if you look at that, you see that 6 out of the 120 measurements deviate in excess of the laboratory's stated uncertainty. All those laboratories stated uncertainties to a confidence level of 95%, or to put it another way, it would be perfectly reasonable to expect 5% of those measurements to deviate in excess of the stated uncertainty. So that's pretty much dead on. That's more or less exactly what you would expect. So what about the simulated real samples if we look at them across the same concentration range? Well, this is the graph for them. So straight away you can see sort of visually we've clearly got more scatter than we had for the synthetic samples. Here we now see that a touch over 40% of the measurements deviate in excess of the laboratory's stated uncertainty. So we have a bit of a contrast there. What might be the reason for this? I guess when you think about what is the key difference between the two sets of samples, it's that the synthetic samples don't contain anything other than chloride, whereas the simulated real samples are likely to contain other species that have been taken up from, the stack sim. So there's, NO2 was present, for example, and things like that. There's other things that have some level of solubility in water. And so this is potentially an interesting observation because, when you look across Europe, there's a lot of proficiency testing schemes that are based on using synthetic type samples where you only have chloride in the solution that is sent out. And so on that basis, we might be getting a slightly optimistic view of the actual comparability we have across the community that EM1911 is providing us. But what about the uncertainty requirement? Is this amount of scatter actually a problem? So for the synthetic samples, where obviously there's a lot less scatter, not at all, I can tell you there that whatever uncertainty requirement you look at, that's not an issue. And so I won't talk about them anymore. For the simulated real samples, then there is more something more interesting, more of a story to tell there. So here I've replotted those simulated real samples, but I've used all the measurements that were across a 0 to 15 milligram range here. So as you would probably have guessed, on a waste incinerator, the limit value is often 10 milligrams. You have a 1.5 multiplier rule for the measurement range, hence the 0 to 15. If you look in EN1911 in clause 8, it will say that the uncertainty required for the overall method is 30% of the emission limit value. So 30% of 10 milligrams gives us plus or minus 3 milligrams as the overall method required uncertainty. And so that can be represented on the plot there with the dashed lines at plus 3 milligrams and minus 3 milligrams that you can see. But obviously we're not dealing with the overall measurement method here, we're just looking at the analytical step. Is there a sub-requirement in 1911 for the analytical step? The answer is no, not a specific uncertainty requirement. So instead we can look at this a different way. We could say, well, we know what the overall uncertainty requirement is. What is a typical sampling uncertainty? Now, of course, it's a bit like asking how long's a piece of string, of course. And so what I have done is sort of consulted with some sampling teams to ask them what they would normally quote for measuring a HCl. And it's a bit of exacting figure, that 7.2%, but that's basically kind of the average number that has come out from asking and consulting with a few different teams, of 7.2% being a typical quoted uncertainty for sampling. Now, I should point out that elsewhere, as mentioned at the start, under the HEROES project, we're going to be looking at the community uncertainty for sampling. So the sampling, variance across, many sampling teams all sampling. And so we'll be able to see in due course how close that 7.2% value is to what we come up with under the HEROES project. But for the moment, that's kind of the best estimate we have. So if we take a 7.2% of value sampling uncertainty away from the overall method uncertainty, then we can see how much is left for the analysis step and how much we need to make sure the analysis step doesn't deviate more than if the overall method's going to comply. So if we take that 7.2% value of sampling uncertainty away from 30% the emission limit value, we get the solid black line. And as you can see on the plot, that doesn't actually change an awful lot. So we haven't got much tighter. That solid black line is only slightly within the plus and minus 3 milligrams. And so we're being quite generous here in leaving a lot of headroom for the analysis step, but it doesn't hurt to be on the cautious side of this analysis. When we do that and ask ourselves how many measurements deviate beyond the solid black line, the answer is just under 10%. And so actually that's not too bad. It's not the 5% that would be ideal, but it's not a million miles away. And so from a compliance monitoring point of view, we might say we're happy with that. The other thing we need to think about is the second key role for any SRM, which is calibration of a SEM system. There are across Europe different sort of national requirements for the implementation of that, and the standard we're talking about here, of course, is 14181. If we kind of look close to home for a moment, in England, what the EA would, and this isn't a requirement, actually it's a recommendation, because the operative word is ideally when you look in the guidance. They say, ideally, the SRM used for calibrating the SEM should be operated at half the uncertainty or better than is required of the SEM system. So SEM systems for measuring HCl would have to comply in the IED with an uncertainty of 40%. So this is where the 20% number comes from. So if we want to operate our EM1911 overall method at 20% of emission limit value, and then we take away our 7.2 sampling uncertainty, we now get the dotted line. So things obviously getting a bit tighter on the plot there. And now we see that just over 20% of those measurements would deviate in excess of that uncertainty. So that's probably not quite where we would like to be. So, but what about back conclusions, which have already sort of been mentioned already today, and obviously emission limits are only going to get stricter. So HL is of course mentioned in a few different back conclusions, but what we've been simulating here is a waste incinerator. If you look in the back conclusions for waste incinerators, you'll see an AEL range of 2 to 6 milligrams. So we can pick 3 milligrams as kind of a challenging target and look at data across a measurement range of 0 to 4.5 milligrams. And so we're just looking at the tests on that level. We can apply the exact same methodology as the last slide and see that from a compliance point of view, about 20% of the measurements would deviate in excess of the 1911 required uncertainty, and just over half of those measurements would deviate in excess of the uncertainty that the Environment Agency would recommend as being necessary for the calibration of a SEM system. Okay, so just to sum up at this point, we've seen that when we kind of have proficiency testing schemes based on samples that don't have interferences, we might be getting a slightly optimistic view of the level of comparability across analytical laboratories that 1911 is giving us. From the simulated real samples, assuming a 7.2% sampling uncertainty, we've seen that at a limit value of 10 milligrams, a touch under 10% of the measurements exceed the uncertainty required for compliance monitoring, and that at the same limit value, a little over 20% of the measurements would exceed what one national regulator, so in this case the Environment Agency, would recommend as the uncertainty necessary for a fit-for-purpose SEM calibration. If we go to a more challenging limit value of 3 milligrams, and those numbers change to a touch under 20% and a touch over 50%. So in terms of the control that 1911 is giving us, probably we're okay with that first scenario, but would be kind of less okay with the latter 3 scenarios. So what can we do about that? If you look in 1911 at the moment, then in clause 8, as I mentioned, you have the overall method uncertainty requirement of 30% of the ELV. You then continue reading that clause, you'll find, and I'm sure lots of people have looked at this many times, this table of sampling requirements. Not all of these necessarily go into the uncertainty budget, but all of them are controlling the method and giving you, quality control to make the sampling as good as it can be and hit a minimum standard. If you then look at the analysis side, it's a bit more light touch. In terms of a specific, numerical requirement, there is a requirement on precision of 2.5%, but bias isn't really considered. It's not really talked about that much. So that's probably something that we should be looking at. So the sort of changes that we might think about making for EM1911 is is kind of on the overall basis, is perhaps recognise that relative overall uncertainty requirement, it can't be maintained all the way down the concentration scale, and Rob Robinson talked about some of this this morning, where it's very clearly that as you go to lower and lower concentrations, the percentage uncertainty blows up. So we ought to, recognise that and give people targets that are realistic. And once we get below a certain threshold, move to an uncertainty requirement in absolute units that stays fixed. We could set a specific uncertainty requirement for analysis, and so augment that analysis table where precision is considered with also an uncertainty requirement. So therefore you're considering both precision and bias, both sources of uncertainty. There could be more guidance of analytical uncertainty sources. Some of the sources are actually, in fairness to 1911, already listed, but probably what we need to think about is what sub-requirements, would it be reasonable to expect and reasonable to give us the kind of control that we need to get the kind of performance we want out of 1911 across Europe. If you have looked recently at the recently published HFTS and formaldehyde TS, and I was on the working groups that produced those, and so this was a little bit driven by me, but not just me, but others as well, who sort of have thoughts along the same line. You will see this has started to happen where an uncertainty analysis is specifically required, and so CEN is kind of heading in this direction. For those of you listening sort of based in England, then you'll probably think, oh, wait a minute, we already have MCerts for laboratories, and you'll be absolutely right with that. And so, but what I'm suggesting here is that obviously some of that, needs to be kind of adopted in 1911 as the, really the overarching standard here, so that we have that comparability on more of a European basis. And again, have those discussions about what kind of additional requirements would we put in 1911 to give us a kind of comparability that we need in that analytical step to be able to monitor at some of the limit values in line with back conclusion type documents. And then the last thing I'd kind of mention, and I know Paul Firth already said this once this morning, which I was really pleased to hear him say that, because I completely agree, in that there really is a growing argument for the revalidation of the HLSRM, the SO2 SRM, dust, and formaldehyde hasn't been validated yet. We really need to have the formaldehyde new TS document validated as well, and so a big revalidation campaign would be, I think, very welcome at this stage, because a lot of these SRMs were validated some 20 years ago, and ultimately what we're trying to measure with them has changed significantly, because the regulation has changed significantly. Okay, I think that's me. Thank you very much for listening.
Thank you very much indeed, Mark. I can't see any questions on the tab or in the chat. I was wondering about one point myself. Maybe it's more of a general point. A lot of the standards have an example uncertainty budget included in them. So that sort of bottom-up indirect assessment, it can only really include what you're aware of in terms of uncertainty sources, as opposed to a direct assessment comparing between laboratories. So do you think there's the scope for including some sort of interlaboratory uncertainty, like a systematic uncertainty, as a number that's added into that sort of budget to account for it?
Yeah, and absolutely there is, and this is kind of what we'd, so if you look in the formaldehyde TS document, we have specified in there that, in terms of determining your bias, then one way of doing that, so it's not the only way you're allowed to do, is things are flexible at the moment, but one way of doing that is via an interlaboratory comparison where you understand the bias, and I guess that's what I've really been was sort of presenting in the data here. This is the point, saying that a sampling team, the uncertainty they're exposed to is the variance across all the analytical laboratories that in principle they could have sent those samples to, and your routine way of measuring that is an interlaboratory comparison, and obviously they do exist. In some countries we have full stack simulators where you can measure the sampling and analysis. Not every country in Europe has those facilities, of course, and so they're more limited to sending out only samples. They can maybe only look at the analytical side, and it's more difficult for them to look at the sampling side. But I think, I think where it's possible, I would support moving more to an interlaboratory comparison approach for people to understand what kind of uncertainties should be, assigned to these kind of analyses. And ultimately we could do the same with the sampling side as well.
Yeah, it was the sampling side I was thinking about, but
Sure.
of course it does apply to both. Yeah.
Yeah.
And I agree with you that the analytical bit is often treated like a black box. And it's just sort of pushed to one side and we'll assign that number to it.
I think, it's kind of, you have those sub requirements on the sampling side in a table. And I think it would be really good if, with analytical laboratories, we could have a discussion about, if we try to put together a table for the analytical side, what would go in it. You're using an ion chromatogram, so what would be your uncertainty requirement of your calibration solutions? What would be your tolerance on lack of linearity? And I know people already, of course, a lot of labs will already be doing that, of course. But then let's standardize that and put it in 1911 to ensure that everybody's doing that, and that national accreditation bodies are accrediting everyone across Europe against the same kind of table of requirements. And so that would be my view.
Yeah, thank you very much indeed. I don't think there are any further points, so thank you again.